So my internet cut out, but I'll hopefully be able to splice this together really well. So where I was I was talking about building the model. I plotted the data. It looks pretty good. Looks like we can easily build it. So now let's try to construct a linear mix effect model for using the snowpack data. So we're interested in looking at kind of year and elevation and how that affects the snowpack. And we're going to use a random effect of site. And so here's our model. So we have our snowpack clean data here. And so we have like elevation and year as fixed effects, and then site as a random effect. And so we're going to use the LMER object from LMER by here times elevation. So we'll look at interactions between the two. And then we'll do a plus, and then this is a random effect term. And so you do it by a one bar and then the name of the site. If you had stuff nested, then you could list it here, but I won't get into that today. And then data equals snowpack. So I'll run this. You'll see it'll quickly just compute the linear effect model. One thing you'll notice is that, right, we're going to want to make sure that we're using not RMEL. Want to use likelihood with it. And so we're going to switch to maximum likelihood model here. So here's our model with the fit and everything. So you can actually get an AIC score here. We won't use that. Have some of our residuals, and here's our kind of models coefficients, or sorry, yeah, the coefficients for each of these terms. You'll see here it says the variables are on very different scales. Consider rescaling. So we're going to do that. And so that's really easy in R. And you want to rescale your continuous variables because they're on very different scales. It can create wonky things in your model. Most of the time I found it doesn't make a difference, but I've seen other papers and work where people have had weird stuff happening because their variables weren't scaled. Anyway, so we can just quickly scale it by using the scale function around each of the continuous variables. And so we'll call this snow model. We'll run that. It'll look better. Shouldn't give us any of those errors that we had before or warnings. And everything looks good. So now let's kind of go through some of the assumptions using LMER, the mix effect model. So first, we can plot just the model and just get, say, our plot to see if our residuals with fitted has any shape to it. So this is a great example of the fanning shape that you find. So this is very heteroskedastic, and we'll have to transform it to get rid of this. So this is not any good. We can look for multicollinearity between the two variables. You can see all these around 1. It's well below, I think, usually 5 or 10, or what the cutoffs people use. So this is fine. No issues of multicollinearity across there. Let's also check our QQ plot. There are some deviations. So there are, I believe, some fatter tails. I can never remember if it's fatter or skinny tails. Doesn't totally fit, but I'm not as worried about that. I am very worried about the heteroskedasticity that we're seeing in this plot. So we'll want to correct this. So one thing you can do to correct it is do some transformation on your response variable. And so I'm just going to quickly add a square root term because I played around with the data a bit and that seemed to fit it pretty well and create a much better model. So I did a square root. I added a little number 0.001. So it's not doing a square root at 0. So I'm going to give me something weird. It was mostly because I was doing other. I think square root 0 would work fine. Maybe let's try without this. I was doing some other kind of corrections, like log transformations, where you would have to do that. Let's see what it looks like. It'd be exciting. Yeah, it fits actually pretty well. So maybe we don't need to use that 0.001 to actually change that from my code. Anyways, this looks better. There is some wonkiness with some of the 0 values here. You'll see that in plots, but it looks much, much better than we had before. So we're going to stick with that. And their Q norm and this should still look pretty good. I mean, actually almost fits almost better than before. So let's stick with this model now. So we built that first model. Make sure all these have REML equals false. I'm going to pull this out so you can see the whole thing better and like what we're doing. So now let's build an interaction model. Let me clean these other ones up. So we're square rooting it. We're scaling our year and elevation. We have a random effect the site, data snowpack, RMA equals false. So we get maximum likelihood. So this is our additive model. Below, we'll just do an elevation only model, a year only, and then we'll have a null model of just one. So kind of like before, we can just run, say, like a type 3 ANOVA as well. And you can see here that we don't see any, so we don't have a significant effect of the interaction. So we'd probably throw this out of the model, but our other main effects are significant. And so that would be a good sign to keep those two main effects. But let's go through the other way. So let's do like the comparison using log likelihoods. So you start with your full model and then you switch to your additive one as your second one. You can see here it's kind of confirms what we saw earlier, where you get the same kind of p-value because it's kind of doing the same thing. And then so it looks like we want to we'll keep this additive model, and let's compare that, say, with like elevation. This was a significant difference, so we want to keep the additive model, and then we can also compare it to the other one, just year, and it's also the same way. So we're sticking with the additive model. It seems really great fit for the data we have. So basically we're saying, right, is we're not doing any interaction turn because it didn't fit it, or the models, the statistical testing to prefer one without adding differing slopes to all of our levels. So now doing the same thing with AICC, we can run all of them together. And then you can see, just to confirm like what we saw before, you have two models that fit the best, which are just your snow model. So if you're with your added complexity of that kind of differing slopes, but the additive model is simpler and actually is a lower AIC. So we would take the additive model. And the simpler models from that are much worse fits. So we're not even going to bother with these because they're not even anywhere close to what we're seeing with the additive model. So if you just run one, you can actually just get the value from it. And so I'm just going to write this quick thing to kind of simply summarize everything. So first we'll do all the AICCs. I'll use this code, takes these, since these are saved as row names in the AICC function, and make them a new column called model. So row names a column is a super nice function for that. And then I'll just, since we can just calculate this as a value and everything's vectorized in R, we can subtract our AICC column to this value here. And then we can actually get the difference, the delta AIC. And then we'll arrange so then they're ordered. If that doesn't make sense, this is kind of just code creating this kind of table for you. So you can see the delta AIC, there's no difference from the additive, so it's 0. But then you can see here the delta AIC for each of these. And these are much higher values. So we're going to stick with the simpler model of the additive. Okay, last thing I was just going to kind of go over. So all these things kind of converge on the same models. Not always the case, but these cases were pretty clear cut. Now I can show you just kind of some quick, like, what if you want to plot some of what the models were saying. So you can use, since we have two continuous variables in our model, or any kind of continuous variable, you would need to use, instead of EM means before, we use EMIP. And so we'll take your model and then we'll do it by year, by elevation. Cove.reduce means that we want to, instead of just plotting the average, we want to actually plot the whole line. So we'll do false. We'll use transform equals response to get it out of the square root transformation that we had before. And then since we could plot every year on it, I don't want to do that. So I'm just going to take like a few years, like 1940, 1960, 1980, 2000, 2020, just to get an overall view. And then lastly, here's some stuff just to clean up the code, because it will create a ggplot for me anyways. So if we run all this, you can see that we're creating model predictions. So the X variable, as I put up here, is going to be year, and then distributed by is our X variable elevation. Year is going to create all these different lines in this. And so you can see in this plot, let's see it here. You can see that the different lines, and let me actually just quickly show you what the model was telling. Increasing amount of snowpack. our elevation is positive. So as elevation increases, we should get more snowpack. And we can see that as both displayed in this plot here. So elevation increases with it. Scale of year is decreasing with it at this kind of constant rate. And so all these lines are equally spaced because of that. And you can see that there is this kind of shape. It's not like a straight flat line. That's because we had to do that when we did the transformation. It creates a little curvature in the line, which is kind of cool. But that curvature was needed because it fit the data much better, and we don't get that heteroskedasticity on the further ends of our predicted values. Cool. So that's like kind of our predicted lines for each, our regression lines created by the model. And say, what if you want to create confidence intervals for some of these lines? You could do it for all these lines. It gets really noisy or hard to see really quickly. So I'm just going to look at 1945 versus 2020 and just run the same thing. The only thing I'm really changing is I'm adding, the other thing I didn't mention above is, I chose these years. So this time I'm going to actually reduce the number of years. I'm choosing to only do a line for 1945 and 2020. And then I'll calculate confidence interval by doing CI equals true. So this will create a pretty similar plot, but it will then show you some confidence intervals, which is also super cool. So here's just a quick plot of that. And so you can also see here where we have sites, because you can see that's where the confidence intervals are being predicted on it. So there's not many sites over here below above 8,500 feet and below 9,000 feet. But overall, you can see there's pretty good. As I mentioned before, right? You can see at the top end, we don't have much data, so that confidence intervals are wider than, say, down here. But it's super cool, as you probably would imagine. Snowpack in February has decreased in comparison from 1945 to last year. So that's just kind of my brief overview into doing some linear models, mixed effect models. You'll dive into more of these when you start doing more time series analyses and taking into account temporal and spatial autocorrelation. But hopefully this gives you an idea of just what you can do with these models to begin with. And I hope this was helpful. Thanks.